Assalamu alaikum class. I hope that all of you are well and safe in your homes inshallah. This is lecture 35 for our course Signals and Systems. This lecture will conclude the properties of continuous time Fourier transform and basically covers the convolution property. We'll be seeing in this lecture that convolution in time is referred to as simple convolution by a book in case of continuous time Fourier transform, and convolution in frequency is named as the multiplication property in your book. So let's proceed. The convolution property for both the time domain and frequency domain can be stated as follows. If a signal x1 of t has a Fourier spectrum x1 of j omega and another signal x2 of t has the Fourier spectrum x2 of j omega, then when both these signals are convolved, their frequency spectra are multiplied. So if the convolution in time is expressed by another signal x3 of t, then x3 of j omega is a product of the individual frequency spectra for x1 of t and x2 of t. We see that this convolution formula has a similar form to the convolution formula for using Laplace transform. That is, convolution in time is multiplication in frequency. Since both Laplace transform and Fourier analysis are frequency domain transformation tools, so the properties remain the same. Convolution in one domain remains, multiplication in the other. Similarly, using duality property, if we say that we have a convolution in frequency domain, then this means that in the time domain the signals are being multiplied. This property can also be stated from a multiplication point of view, and that is why your book has named it as the multiplication property. If we have two time domain signals which are multiplied, then the spectrum of the resultant signal, say x4 of t, is going to be the convolution of the individual spectra x1 of j omega and x2 of j omega. So if in the time domain two signals get multiplied, in the frequency domain their spectra get convolved. Now in the following slides we'll be seeing some examples for both time convolution and frequency convolution, or some applications of the time convolution property and the frequency convolution property. So time convolution property can be used to determine the output of an LTI system. We know that for an LTI system, the response or the output y of t is given as a convolution of h of t, and which is the impulse response of the system, and x of t, which is the input. So the Fourier transform of the output would be h of j omega, which is the Fourier transform of the impulse response, and x of j omega, which is the Fourier transform of the input. So the Fourier transform of the output will be a product of the Fourier transforms of the impulse response and the input. So this property can be used only if the system is stable, because we know that the convergence of Fourier transform is only guaranteed under certain conditions which are known as Dirichlet conditions. So we know that an LTI system is stable using the basic definition from chapter 1 if the impulse response h of t is absolutely summable, or if in case it's an exponential, it's a decaying exponential. So if we look at this property, we know that this property is the same as one of the Dirichlet conditions. So if the other two Dirichlet conditions, which concern the number of discontinuities, are valid, then h of t will have a Fourier transform. So most of the systems we encounter will be stable systems, and for them Fourier transform will be possible, as at least as long as you're doing undergrad. But in case if you have a system which is unstable and which does not have a Fourier transform, we cannot use Fourier analysis, and in that case you have to revert to Laplace analysis. So, time convolution property can also be used to simplify LTI system interconnections. So, if we have two systems connected in cascade, the resultant Fourier transform is a product of the Fourier transforms, and this is the commutative property. It can also be the first system comes later and the second system H2 of j omega comes earlier. Since Fourier transform obeys the laws of linearity, so the parallel interconnection and the feedback interconnection takes a similar form as we have done for Laplace transforms. Let's look at some uses of frequency convolution. So the first use of frequency convolution is in the process of modulation. Modulation is a process which is frequently used in communications. What happens is that a signal, a low frequency, generally a low frequency signal, known as the message signal, is used to modulate a high frequency signal. By modulate, we mean that the envelope or the periphery or the boundary of the high frequency signal takes the shape of the message signal. So that is known as modulation. Modulation is done so that the frequency of the low frequency signal is changed such that such a signal can cover larger distances as compared to an unmodulated signal. Rest of the details of the modulation process you will study in communication systems course, inshallah. So when we multiply two signals, say a low frequency signal or a signal u of t is being multiplied by a cosine wave, which is generally the case. Output y of t is u of t cos of omega naught t. Now the Fourier transform of the output y of j omega would be a product of the Fourier transforms of the input signal and the cosine wave. So using the frequency convolution property, in substituting values, substituting the transform for the Fourier transform for the cos wave, which is cos of omega naught t as a transform of pi del omega minus omega naught plus pi, which is the amplitude of del omega plus omega naught. This is an impulse which occurs at frequency omega is equal to omega naught, and this impulse occurs at frequency omega is equal to minus omega naught. So as a result, when both of these two functions get convolved, we remember that convolution by an impulse implies that your function appears at the instant of the impulse. So you have half u of omega minus omega naught plus half u of omega plus omega naught. So the transform is going to look like this. U of omega, after being convolved by this impulse train, gives this modulated signal. Now we see that the original signal had a carrier frequency, had a base or had a center frequency of 0, but now after the signal is modulated, it appears at frequency omega naught and minus omega naught. The second use of frequency convolution is in frequency selective filtering. We have already discussed filtering as one of the most important applications of signal processing. So one of the four categories of filters we discussed were the bandpass filters, where bandpass filters are a set of filters which only allow a set of frequencies to pass and reject the other set of frequencies. So such a frequency shaping is possible if we say that the frequency response of the circuit is, or the frequency response of the system is 1 at the desired frequency and 0 otherwise. Now if such a filter is designed in hardware, we require components such as resistors, amplifiers, capacitors, etc. So designing a filter with variable center frequency in case we have multiple signals coming, and say we have a conventional radio and we tune it to one frequency and then we tune it to another frequency. So making such a tunable filter is difficult in hardware. So such a filter can be designed by, say, we make a filter with fixed frequency and apply amplitude modulation or multiplication as a second step. So let's see the structure of such a system. For example, we have an input signal x of t and it is being multiplied by an exponential j omega ct. Now multiplying it by the exponential e j omega ct gives us the output signal y of t, and we know that by virtue of multiplying this signal by the frequency, say carrier frequency omega c, the the Fourier transform of the signal y of j omega will be shifted from the frequency of xt to the frequency of this complex exponential. So we pass this signal through a low pass filter and we get an output w of t. At the output again we multiply this output by another complex exponential, but this time it has a frequency minus omega c, e minus omega ct, and we take our output ft. Ft is wt into e to the power minus j omega ct. So in the next slide we'll see what happens from a frequency domain perspective. Say our original signal x of j omega was a baseband signal, it was at a frequency, it was centered around a frequency of 0. So once this signal is filtered, in fact before filtering, say we obtain y of j omega. So as we discussed, y of j omega will be the signal shifted at a frequency from a frequency of 0. The signal will be shifted to a frequency of omega c. So now it appears at omega c for y of j omega. So once we filter the signal through the low pass filter, where the low pass filter has a frequency or has a bandwidth of from minus omega naught to omega naught, it has a bandwidth of 2 omega naught. So let's pass this through a band pass filter, a low pass filter. So now we get this selected portion of signal which we wanted. So we remember that fg omega was, or f of t was omega w of t multiplied by e to the power minus j omega ct. So the Fourier transform is a convolution of the two Fourier transform, and convolution by an impulse implies that now this response will exist at a center frequency of minus omega c. Why I am referring to it to a center frequency is because in the individual spectrum, the spectrum was centered at a frequency of 0. Now after modulation, the spectrum is centered at a frequency of omega c. By centered means that it is symmetric around this point. Obviously at this point the spectrum is not centered at any frequency because its shape is different, but now the spectrum is shifted to the frequency of minus omega c. So now the original signal is tuned to another frequency. So in this way, band pass filters can be implemented simply through using the multiplication property. If you want to explore this property further, that is to see what happens if we want to have a real signal, because the signal is not real, you can explore in your book in detail, because they have given further examples to show you if you want to have a real signal, how does the modulation property or how does this circuit simplify. So we can summarize that by passing the resultant signal through a low pass filter and then multiplying it by an exponential e to the power minus j omega ct, we have achieved the bandpass filtering operation. So such a bandpass filter is centered at the frequency minus omega c, which is the frequency of the exponential you're multiplying it with, and it had a bandwidth of 2 omega naught, because the low pass filter you used had a bandwidth of 2 omega naught. So filtering, band pass filtering can be achieved in 2 steps in this way. So if we vary the frequency omega c, the center frequency of the band pass filter varies, and we can tune different bands. Now after these discussion of the usage of convolution in signals and systems, we are going to solve 2 examples to see how the convolution property is applied to mathematical signals. So class, we will be solving 2 examples to see the applications of the convolution property. This first example deals with the time domain convolution. So let's say that you are given an LTI system with the impulse response h of t is e raised to power minus at u of t, and x of t is equal to e raised to power minus b of t u of t, and you have to determine the output of the system. We know that for an LTI system, the output y of t is given by y of t is equal to x of t convolved by h of t. When you are not mentioned any method, you can do any method you like. For example, this example can be solved through the time domain convolution techniques we have discussed in chapter 2. However, if you are asked to adopt a frequency domain strategy, you can either use the Laplace transform or the Fourier transform, because we know that in both the techniques, convolution becomes multiplication. But if you are asked that you are to use, say, Fourier analysis particularly, then you will be using Fourier transform to determine the output of the system. Say for instance, over here, you are not asked to determine the convolution, you are asked to determine the frequency response. So that means after the convolution, you have to get the frequency response. In that way too, you are free to choose any method. So say for this example, you are asked to use the Fourier analysis techniques to determine the output. So we'll be proceeding by converting this convolution in time to multiplication and frequency. So y of j omega is equal to x of j omega, h of j omega. Now from table 4.2 of our book, the 13th signal set is e raised to power minus at u of t. So e raised to power minus at u of t has a Fourier transform of 1 by a plus j omega, given a is greater than 0. Why is this condition mentioned? This condition is mentioned because when we were discussing the convolution property, we said that an analysis of the system through Fourier techniques is possible only if the system is stable. If the system is unstable, we cannot use this analysis. So for a positive exponential, for a greater than 0, this exponential e raised to power minus at is a decaying exponential, which means that its result approaches 0, or its integral approaches integration, the value approaches 0 as time t approaches infinity, or the integral converges. So that is why a Fourier transform of this signal is possible, and it can be analyzed through Fourier analysis technique. Similarly, the Fourier transform for the input signal e raised to power but minus b is b plus j omega, given b is greater than 0. This is given as an input condition, so we can simply use it. And again, since this input is also bounded input, bounded output, input is bound, so output is going to be bound. Now the output is simply, the Fourier transform of the output is simply a product of these two, which is 1 by a plus j omega into b plus j omega. Since we have solved such questions through Laplace transform, so we know that the natural next step is to divide this y of j omega into partial fractions so that its inverse can be taken easily. Y of t can be determined easily by inspection through the table. So this is a by j, a plus j omega plus b by b plus j omega. Once we solve these through partial fraction expansion, we'll get a is equal to 1 by b minus a and b equal to minus 1 by b minus a. So substituting the values of a and b in y of j omega, we get y of j omega is equal to 1 by b minus a into 1 by a plus j omega minus 1 by b minus a for the b term, 1 by b plus j omega. So I'll be arranging the terms such that 1 by b minus a can be taken out, and we have 1 by a plus j omega minus 1 by b plus j omega. Now to determine a time domain expression for this, we take the inverse Fourier transform, again through comparing it with the Fourier transform set 13 in table 4.2, we get this is equal to 1 by b minus a, e minus at, u of t minus e raised to power minus bt u of t. So again, like always, we see that frequency domain techniques simplify the process of convolution. If we were convolving these two decaying exponentials, we would have done it through, if we had done it through a time domain way, we would be having a region with no overlap, then a region with partial overlap, then the partial overlap continues. Whenever we are using frequency domain techniques, one further advantage is that we can get a simple expression or a straightforward expression, time domain expression. Otherwise, we have seen that when we use time domain techniques, we get ranges. We generally don't get a time domain expression this easily. Now, say for instance, for this particular example, both the input and the output, both the input and the LTS system had the same complex exponential being multiplied. Say both h of t and x of t were equal to e raised to power minus at u of t. Excuse the projection of the camera. Actually, there's a time delay, time lag between the camera and my voice, so it's kind of difficult for me to synchronize the video on the go. But I hope that you are following me so far. So if both A and B are equal, A is equal to B, so for y of j omega, we would have had a y of j omega is equal to 1 by A plus j omega square. In that case, we have seen it through example 4 in lecture 33 and 34, and also from the Fourier transform pair 14 in table 4.2. We can see that for this case, y of t, or the output, would be equal to t e to the power minus at u of t. So we see that through using Fourier techniques, we can solve time domain convolution simply by going into the frequency domain. I'll be taking a snapshot of the solved numerical and placing it on the slides, placing it on the PowerPoint so that you can have it afterwards. Now, for example 2, or for the frequency convolution example, we have to use the multiplication property to determine the Fourier transform of the signal given by xt is equal to sine of t by 2 by pi t square. Now if we look at this expression, we can see that this x of t is a product of two cosines, or which means that in the time domain there must be, if there is multiplication in the frequency domain, there must be convolution. So first of all, let's decompose this time domain signal into individual sinusoids which are being multiplied. So x of t is equal to sine of t into sine of t by 2 divided by pi t square. So I decompose this into two sinusoids or two individual terms. This is equal to sine t by t, which is the first term, and if we look at it carefully, we can see that this is a sinc term, into sine t by 2 by t. This is the other sinc term, into 1 by pi. Now class, I'll pause here for a second, and I just want you to know that in your book the sinc is defined as sine of pi t by pi t, and so far as we are going, I have defined a sinc as sine t by t. Both representations are the same, are okay. One is known as the normalized sinc and the other is known as the unnormalized sinc. In any way, sine of t by t or sine of x by x is a sinc. By normalizing it, the zero crossings can be handled so that they are not a function of pi anymore, they are a function of numbers 1, 2, 3. So in any case, sine of t by t is a sinc, and sine of t by 2 over t is a sinc, because in both cases the argument is a function of t and they are being divided by the same variable t. So since we are asked to determine the frequency response of this, the frequency domain, the Fourier transform of the signal, so we know that whenever in the time domain two functions are multiplied in the frequency domain, their transforms are being convolved. So let's say we name the first function as x1 of t and we name the second function as x2 of t. So say this is our x1 of t and this is our x2 of t. So in the frequency domain, what happens is x of j omega is equal to 1 by 2 pi This is the formula. x1 j omega convolved by x2 of j omega. Now we have been doing this example so many times in the Fourier transform chapter 4, Fourier transform chapter, that we know that whenever we have a sink in one domain, we have a pulse or a gate function in the other domain. So for this sink in the time domain, in the frequency domain, we have pulses. So using the Fourier transform pair, which is the pair, let me find the number dash. So using the Fourier transform pair 9 from your table 4.2, or otherwise we have done it in example 1 of lecture 32, example 6 of lecture 33-34. We know that the Fourier transform pair sine omega t by pi t equals rect t by 2w, should be w by 2w. So where capital W is the width, and for rectangular function, this implies that the function has say the function occupies with capital W on the positive side and with capital W on the negative side, because this is 2W. So if we substitute, if we compare our input expressions, we can say that x1 of t, for x1 of t, which is equal to sine t by t, the Fourier transform x1 j omega is pi rect of w by 2. Now I have taken this pi from the left, because this pi is a multiplier, it's a scalar multiplier, from the left side, division from the left side and multiplied it on the right side. Because scalars, Fourier transform is a linear operation and scalars multiplied on either side is equal. So let's say that you divide both sides by, in fact you multiply both sides by pi. So pi gets cancelled here and it gets multiplied on the right side. For the second time domain function x2 of t, which is sine t by 2 by t, we have pi rect w. So how do these frequency domain functions look like? The first function, rect w by 2, the denominator, as we have discussed, tells you the width of the gate. So it is plus 1 here and minus 1 here because the width is 2. And for the lower function, since its total width is 1, so half of it is on positive side and half of it is on the negative side. And since this is a function of omega, so we have omegas here. Now coming back to the expression, let's substitute the values in the x of j omega expression to get the expression. So x of j omega is equal to 1 by 2 pi rect w by 2 into pi rect w, and if you see this 1 by pi This 1 by pi got missing on the next line, so I'll write it here. And in the lower expression, I'll write it here. So 1 pi and 2 pi in the denominator and 1 pi and 2 pi in the numerator. They get cancelled, and the resultant expression for x of j omega is 1 by 2 rect omega by 2 convolved by rect omega. So now we have to convolve both these functions to get the expression for x of j omega. We have done convolution a lot of times. I'll just be debriefing you how to do convolution because the figure in your book is not right. So we'll briefly go through the ranges of the signal and we'll discuss the shape so that you know that how do you get ranges and what's the shape. So whenever two rectangular pulses are convolved, we get a triangular function or kind of a triangular function depending upon what's the width. If the width of both the pulses is same, we get a triangular function, and if the width of pulses is different, so we get increasing slope representing partial overlap. Then for the full overlap we get a flat top, and for the again partial overlap we get a decreasing slope till we get 0. So for this particular function, let's convolve it and see what ranges on the x-axis we get. Since both the pulses have different width, so obviously we'll get a function similar to the top function here. So what are the steps of convolution? We change variables. So say the larger function, it becomes a variable of say tau, and we say it's rect tau by 2. You have to remember that these are the frequency domain functions which are being convolved. And for the other function, the smaller function, say that it is the one which gets flipped and slide. So first of all, when it gets flipped, we have rect minus tau by 2, sorry, minus tau. This is a function of rect. This is rect w, because this is rect w. If we see here, this is rect w. So now this w becomes a function of tau or minus tau. So since it's a pulse, even if it's flipped, its form remains the same. And what's the second step? The second step was we get rect of w minus tau. Please see that I have replaced t by w because this is a frequency domain convolution. Convolution is the same. Obviously convolution, the process of convolution is the same if you're doing it in time domain or frequency domain. There's a change of variables, then there is flip and slide. You flip the function and see where the functions overlap and we get ranges and so forth. So this edge becomes omega plus 0.5, since this is plus 0.5 here, and this is omega minus 0.5. Now when we are convolving these two functions, we know that there will be a start of convolution, and after the start of convolution we will be having a partial overlap. The partial overlap will continue. So when's the partial overlap start? When does the partial overlap start? partial overlap starts when this omega plus 0.5 is less than minus 1. So it starts when omega plus 0.5 is less than minus 1 or omega is less than minus 1.5. After this point, omega is less than minus 1.5, our partial overlap will start. So, and this partial overlap will continue till this trailing edge W omega minus 0.5 is less than this minus 1. So this continues till omega minus 0.5 is less than minus 1. This implies that omega is less than minus 0.5. So the first region, the partial overlap, is from minus 1.5 till minus 0.5. Then we have a region of full overlap. Now this full overlap will start once this omega minus 0.5 fully overlaps with this function, and this will continue till this trailing edge, this right, in fact leading edge, omega plus 0.5 goes beyond this 1. So this full overlap continues till omega plus 0.5 is less than 1 or omega is less than 0.5. So what is the range of full overlap? Minus 0.5 I told you class, this at the final point you can either take an less than equal to at one point, then for the other point you will take greater than. Even if you put equal to symbol here, the expression for the integral gives you the same result. So it doesn't matter, but you just it's a good practice that for one limit you use less than equal to, and for the other limit you use greater than. Or for one limit you use less than, and for the other limit you use greater than equal to. So equality comes at one at either edge. Then again we have the partial overlap region. And this partial overlap starts when omega is greater than 0.5, and this will continue till this omega minus 0.5 is less than 1. It goes outside 1. So we say that omega minus 0.5 is less than 1. So this continues till omega is less than 1.5. So for the next partial overlap region we have 0.5, which completes our regions. So we can say that the resultant waveform will start at minus 0.5. Let's use another paper because I am unable to focus this paper. So the three regions, we have the ranges minus 1.5 less than omega less than minus 0.5, and when you make an integral yourself you will know that the integral has a rising waveform. Then for the other region, this is the partial overlap region. For the full overlap region we have the range minus 0.5 less than omega and 0.5 full, and for the third region we have 0.5 again partial 2. partial 1. So when we plot this, it starts from minus 1.5 till minus 0.5, it increases till 0.5, it remain constant, and till 1.5 it will decrease. Now I leave it to you to see whether the Fourier transform forms this waveform or not by writing integral equations and solving those integrals. I'll just summarize the starting and ending points. Whenever two pulses are convolved, the starting point is always going to be the sum of starting point of these two, and the ending point is going to be the sum of ending point of these two, and the middle point or the flat top is going to be equal to the length of the smaller pulse. So this concludes our lecture. Given at the end of this lecture are the numericals you're going to solve for convolution. There's one lecture for this chapter 4 left. We'll be doing that lecture in the forthcoming week, this week. So this week we'll end our chapter 4. In case you have any problems or any queries, you can always email me, text me and ask, and I'll be responding you inshallah. Allah Hafiz.